So one of the first things we think about when making a thematic map is using symbology and using color and using shade in order to actually communicate effectively. Better color scheme now, light to dark, right? So our brain's processing this and saying, all right, light means less and dark means more. So we're working with our natural perceptual and cognitive systems to make the map reading task much more easy for people to understand. But there's kind of one problem with this map. This map is mapping totals, as you can see in this sort of legend up here on the left. And because of the problem of geography, large states, small states, large counties, small counties, and because of the differences in population density, then we need to account for that difference somehow in the map. And this is what we do by referring to something that we call normalizing your data for a Choropleth map. Choropleths don't work with totals. What they do work with are rates, ratios, proportions, and so on. Percentages.
So again, this is the same data, only normalized?
Yeah, exactly the same data.
Okay.
So now it's the number of Republican votes.
It's almost exactly the inverse of the map that we were seeing previously.
Yeah, which is kind of interesting in its own right? Yeah. So we've got the number of Republican votes as a proportion of the total votes in each county. This is a more truthful map because we're now taking into account different population densities. Okay, that's natural breaks. Now, what is natural breaks? It's one way of classifying the data, and you can see we've kind of binned it into 5 separate classes, each of which has a class interval or boundaries. And if the data point falls within each of these classes, that's the color in which it's drawn. And that's how we get the light to dark.
Womp womp. Ken, you probably know this, but you and I differ in our opinions of natural breaks. You love natural breaks, and it does a good job of chunking out the data, but I just don't like it. It seems kind of mysterious and occluded, and it's like a black box. It's like some algorithm that breaks up a histogram into where it thinks gaps are, and I'm like, yeah, but you don't have nice rounded numbers. You don't have even groups. It's really sneaky. I think it's sneaky. You'll have a good looking map, but it's sneaky.
It's algorithmically sneaky, right?
Yeah.
So it uses an algorithm based called the Jenks algorithm. And you're right, it tries to look for gaps. So it tries to group values that are of similar character. And that's really what a Choropleth is trying to do, show areas of similar character. But hey, okay, you don't like it. What would you go for instead?
It depends on what I wanted to show. I'll tell you, if I wanted a guaranteed good-looking map, I would pick Quantile, which happens to be next on your list.
Yeah, well, let's take a little look at that and see how that differs. And the point here is that each of these techniques changes the appearance of the map. So what do you want to pick out? What do you want to highlight? What do you want to mute in the map? What's the general story? Each of these different techniques, and we're not going to look at them all, but they all have a different impact on the data itself. So this map looks different to the previous one. I'm just going to open the symbology pane, and you can see now that these values are different. And in fact, what we've got with the Quantile with 5 classes is 20% of the data values go into each of these classes. And you prefer that, John?
Well, I prefer it to natural breaks, but it depends. If I wanted to tease out nuance, Quantile's a good option. A way I describe it is evenly filled, unevenly spaced buckets.
Another good reason for using a Quantile is if you're comparing several maps.
The counterpart to Quantile, which I think you're about to click, is equal interval. And the flip side of that is equal interval is equally spaced buckets, but they're unequally filled.
But there we are, there's equal interval. So the takeaway just from here is, experiment with the different classification techniques, the number of classes. What's a good number? I mean, the rule of thumb is between 5 and 7, or 5, 6, or 7. Any more or than that, and you struggle to identify individual colors on the map. Too few, and you're basically just overgeneralizing the data.